So in this question, we'll do our analysis, Oizerga analysis. Origin, 210, 2010, 0. So we have a normal origin, y-axis velocity, x-axis time, both in normal units. So we'll read questions about velocity and time. The gradient, delta v over delta t, is the acceleration, and the area is v delta t, which is the displacement, delta x. What we might note is the slopes are parallel to each other. The lines are parallel to each other. The slopes are equal, so they have the same acceleration. This one starts with a 0 velocity and travels quickly. This one, at time 0, we don't have data, but if we extrapolated backward, would seem to have a negative velocity that would decrease to 0 and then increase in a positive way. All right, so an object is dropped from the top of a building near the Earth's surface. After 2 seconds, a second identical object is dropped. All right, so this is the one that's dropped at time 0, and it accelerates, and we can see then that we have 40 meters per second is the change over 4 seconds, so the acceleration is 10 meters per second squared, which is what we'd expect for something under free fall, which means that's the acceleration of this one as well. A second identical object is dropped from the same building from the same height. So 2 seconds, and then we drop another one. So that's why this one starts at 2 seconds with a velocity of 0. So there is no data back here. It wasn't moving back there. It started, it instantiated here at 2 seconds. After 4 seconds, the first object strikes the ground. Okay, so that's the ground. The graph shows the V. What is the acceleration of the center of mass of the two object system from the moment right before the first object hits the ground? At the moment right before it hits the ground. Now, what we know is the center of mass of object 1 has an acceleration of 10. And object 2 has an acceleration of 10. So wherever they are, that center of mass still has the same acceleration. So the center of mass acceleration is 10 meters per second squared. The whole system is accelerating at 10 meters per second squared. If we took these two bodies that maybe after 2 seconds look like this, if that's our system and we combine them into one object whose center of mass is there, that center of mass is accelerating toward the center of the Earth with an acceleration of 10 meters per second squared. It doesn't matter how many objects or when they are launched, as long as they're all in the air and all moving, being accelerated by gravity, then their center of mass is accelerating according to gravity. So in 7, we have a picture, and it looks like there's object X and object Y. It looks like they're tied by a string, and this says it's the center of mass. So if that's the case, then these must be identical objects. So what we would know then, if this thing is on an inclined plane and released, the whole thing would accelerate. The center of mass would accelerate according to whatever the acceleration would be on that inclined plane. We can replace this whole system with just one body represented by that blue dot. Next, we have a graph. So we'll do our Oizerga analysis. Now, this is velocity in meters per second. So velocity, our origin here is 0, 0. X-axis in time, so we'll read velocity in time, and the gradient delta v over delta t is acceleration, and the area is v delta t, which is the delta x. All right, so identical objects, x and y, which we inferred from the picture, tied together, placed at rest, so v0 equals 0. String has a length of 2 meters. It's released from rest, and the graph of the velocity at center mass as a function of time is shown in the figure. If the string was cut and object y was released from rest while object X was held at rest. All right, so now we've got to imagine this a different situation. If the string was cut and object Y was released from rest while object X was held at rest. So that means there's going to be a delay in X being released. Which of the claims is correct about the new acceleration of the center of mass of the system compared to the original acceleration of the center of mass of the original of A? The new acceleration will be greater than A. Well, right off the bat, we should know that that can't be true. This whole system is going to accelerate because of gravity and how that gravity is affected by the angle. We can't exceed gravity, nor can we exceed the acceleration unless we applied some other kind of force pushing on it. So A is a nonsensical answer. A will be less than the original. Well, if we can picture what will happen in this scenario, is that now X is going to remain steady and Y is going to move, like so, down the inclined plane. Now, the center of mass of Y is going to accelerate like so. But since this one is staying put, object X is staying put, Y is now moving past, but all of the mass is not accelerating down the inclined plane. Only half the mass is accelerating down the inclined plane. So the acceleration should definitely, of the center of mass, should definitely be less than the original. It looks like B is our answer. A new will be equal to A original. Well, we just kind of argued through that to see that if it's true that the acceleration, if X is being held steady and Y is moving, then although Y is accelerating, the weight of the position of X is being holding the acceleration back. So it can't be equal. Cannot be determined. Well, that's false. We've determined it. So our answer is choice B. It will be less. Our next graph, another velocity time graph. Our origin is normal, y-axis velocity, x-axis time, so we'll read velocity time. The slope, delta v over delta t, is acceleration, and the area v delta t is meters per second times seconds or meters, so that's the displacement delta x. So we've got a rock drop from the top of a cliff. So that means v0 equals 0. Downward direction is the positive direction. So downward is positive. So this is positive and this is negative. So that means that g is positive 10 meters per second squared. The graph shows the velocity as a function of time. What would be used to determine the total distance traveled by the rock after 4 seconds? Well, the distance, that will be the area. The maximum value of the curve, no, that would be the maximum velocity. The area under the curve, yes. The area under the curve, as it states that the rock traveled 80 meters in total. I don't know if it says 80 meters in total. I'm not sure where that comes from. But it would be the area under the curve. The slope of the curve is the acceleration. No. The answer cannot be determined. Again, false. It's going to be the area. But as it states that the rock traveled 80 meters total. 4 seconds. The area of this would be 1/2 base times height. 1/2 4 times 40. So that would be 2 times 40, which is 80. So that's where that 80 comes from, but the fact that it's 80 is irrelevant to the question. It's really just that it's the area under the curve. Number 9. So we've got a solid metal, and a hollow plastic ball in a large vacuum chamber. Aha, so this is Brian Cox's video, just like we watched. After each has fallen 1 meter, they both have the same inertia. Well, inertia we know is related to the mass. Same external radius, so if one is made of plastic and hollow and the other is metal, they will not have the same mass, so no, they will not have the same inertia. After they've fallen 1 meter, they'll have the same speed. Now, the momentum is mass times velocity, so since they don't have the same mass but do have the same speed, it will not be momentum. Kinetic is mv squared. They'll have the same velocity but not the same mass, so it won't be kinetic energy. And the change in potential energy is mgh, which you don't know yet. And, of course, the AP has coded this as the wrong question. It doesn't belong in this topic. But we can see positively that it will be speed, that's the answer. Potential energy is mgh. They'll have the same h, they'll have the same g, but not the same m, so it can't possibly be that. And 10. So we have a blue sphere and a red sphere, same diameter, reach from the top of a ramp. So we have a blue sphere and a red sphere. Same diameter, release from the rest at the top, so V0 equals 0. Red sphere takes a longer time to reach the bottom of the ramp. So when it's all said and done, blue is done and red is still going. Sphere is then rolled off a horizontal table. At the same time, so then it's then. Now the blue and the red are rolled off the table at the same time with the same speed and fall freely to the floor. So they both roll off. Which sphere reaches the floor first? Well, it doesn't matter what shape they are, or what size they are, or what they're made of, what their mass is, all of that. They will hit the ground at the same time. The sphere with the greater mass falls, the blue sphere falls, the red sphere falls, neither. They reach the floor at the same time. Choice D.